With two example questions. The first one is from 2011, question 8, part B. You might go to the question, but it looks like that. A square lamina PQRS of side 60 centimeters, mass M, can turn freely about a horizontal axis through P perpendicular to the plane of the lamina. So think about it like there's a pin in P, and then you just give it a little, you leave it go actually, and the thing will rotate, as in spin or hang, so that P will be vertically above R. Lamina is released from rest when PS is horizontal. Find the angular velocity of the lamina when PR is vertical. So remember your steps here. We need to get the moment of inertia. We need to find out how far the center of gravity drops as well. So we're going to get the moment of inertia through P perpendicular to the plane. So the moment of inertia for a flipping square through P. But we don't have that. What we do know, however, is the moment of inertia along the line through PS. So that's a flipping moment of inertia is 4/3 ma. So let me fill in the m is m anyway, and the a there in the formula is half of the side length, so that's 0.3. Let me fill in those. Because it's a square, we also know that the moment of inertia of the square about PQ is the same. So now what we have is the moment of inertia about two axes that are perpendicular to each other and are touching at the point P. So we can use the perpendicular axis theorem, add the two of them together, and that will give me the moment of inertia about P perpendicular to the plane. So I've gone from two flipping axes, one where the axis of rotation is PS in the plane of the particle, the other one through PQ in the plane of the particle, to a spinning axis through P exclusively, and the square can rotate around. And the second thing I need to do is look at the height drop. So if you look at the little diagram on the left hand side there with the diagonal from P to R, right now PS is horizontal and the center of gravity is 30 centimeters below that. Okay, when you leave it drop, then PR will become vertical and the center of gravity will be half the length of PR. So what I'm going to have to do is find the length PR, half the length PR, and then from that half length, I'm going to subtract off the 0.3 from it. You may need to draw the diagram in two positions to verify this, but H works out as that. Okay, the next part then, to find the angular velocity when it's vertical, we just use our energy equation. So the loss in potential equals the gain in kinetics, so mgh is equal to a half I omega squared, and we're looking for omega. So sub in my values. I have a half I, so 4/3 m by 0.3 squared plus 4/3 m by 0.3 squared. That is the moment of inertia through PS in the plane of the particle plus the moment of inertia through PQ in the plane of the particle added together. That will give me then the moment of inertia through P perpendicular to the plane. So they haven't even completed the perpendicular axis theorem formula to get a single moment of inertia. They've just left it separate. On the right hand side then we have our H, and look, when we solve them for W, W works out as a particular value. Okay, that's example 1. Example 2, 2009 question 8. Here's the question. And there are two parts. Part 1 is leading us on to part 2, because in part 2 we're looking to find the maximum angular velocity of the triangle, and to do that we need the moment of inertia, which is part 1. So let's start with part 1. Find the moment of inertia through A perpendicular to the plane. So there are 3 triangular rods. We're going to get the moment of inertia of all 3 and add them together. So AB, moment of inertia, is 4/3 ml squared. AC, moment of inertia, 4/3 ml squared. And we know that because we know the moment of inertia about the end of a rod of mass m and length 2l, and we're told that each of those has mass m and length 2l. It's the rod BC. We need to get the moment of inertia about it through the point A. So get the moment of inertia of BC through its center, that's 1/3 ml squared, and then use the parallel axis theorem to shift the moment of inertia from the center of gravity of BC over to A. All right. You're probably asking then, how do we know how far to shift it over? Well, look at the diagram there. The length from C perpendicular to AB is given the distance D. And what you have there is an equilateral triangle. So the vertical line from C to the horizontal rod AD bisects the line AB. And you can use Pythagoras to find out that D is equal to L root 3. Now that's the same for all of the other rods as well. So the perpendicular distance from BC to A is also that D value. So to get the moment of inertia of BC about the axis of rotation through A perpendicular to the plane of the diagram, you're going to use a third ml squared for the moment of inertia of the rod BC through its center, and then you're going to shift it, so using the parallel axis theorem, plus m by d squared. Now what they've done there is they've added all three moments of inertia together. The first two are the moments of inertia of AB and AC about their endpoints, and the last one then is moment of inertia of BC, and then the plus md squared is just using the parallel axis theorem. All right, second thing we need to do is get that's part one. Second thing we need to do is get the height drop. So the triangular frame is like that initially, and then it rotates to something like that. Now that'll be when its angular velocity is a maximum, because that's when its center of gravity will be the lowest. So what you need to do is find out the height drop. That's where the center of gravities are for those triangles. And remember that the center of gravity splits the vertical height in the ratio of 2:1. So that means the height from the top red line to the line AB is a third of the total vertical line, and the distance from the bottom red line to the tip of the triangle in the second triangle is 2/3 of that vertical line. So what it is the H1 is equal to 2/3 of D minus 1/3 of D, which is just 1/3 of D. Okay, we have the moments of inertia, we have the height, so we go to the energy equation. Remember that the total mass is 3m because there are 3 rods in there, and then when we make our substitution, W works out as that. You can see there are 2 square roots in the final answer, and that's perfectly acceptable.